Hi everyone, thanks for joining us on this lovely Thursday for a special guest webinar that we have today. We have the pleasure of having with us Ami Shah, founder of AppNano, who's enjoyed a long and successful career up until 97. He was head researcher, professor at IIT in Delhi, India, teaching microelectronics and MEMS technology. After that, he moved to the US and worked as a researcher at UC Santa Barbara with, amongst others, Professor Paul Hansma. And he was director of probes at Vico, now Bruker, up until 2004, when he founded AppNano and has been its head ever since. And today, he will talk to you about scanning thermal microscopy. And we have Dr. Patrick Fredericks, our head of applications at Nanoserve, joining him. He's here to answer any Nanoserve specific questions you might have later in the Q&A. Speaking of which, you can submit your questions at any time throughout the webinar through the Q&A tab, and then we'll get to them at the end after Ami's presentation. So Patrick, did I forget anything?
No, I think you summarized all the important facts. So I'm looking forward to the presentation of Ami. We know each other quite some years now, and I've also been testing the setup in Santa Barbara or in California, and we've had it here for testing. So it's a cool instrument, and I'm looking forward to the presentation.
Okay, let's go.
So,
hi there, good morning, good afternoon, and good evening in some places. Thank you for the opportunity to Nanoserve for allowing me to use their platform to present the research on the scanning thermal microscopy module, which we developed a few years ago. But before I move to the STHM, I just want to introduce the company. And what we do here is we make the probes, all kind of the FM probes, which you can think of, or we're using every day, including the scanning thermal microscope module. And the module is one of our flagship product, which we have been supplying for various applications. This next slide, without spending much time, I just want to show you a collage of the probes which we make. One of the probe which we take pride in making this access probe, which is very good for terse applications and seeing the probe tip while you are scanning. So this is one of the unique probe where no probe like that exists in the market. The angle here is about 18 degrees, so this is something which we feel is very different than the other probes. Other probes are like normal, which people have been having. So if you have any questions about probes, you can let me know or email or. But for all Nanoserve users, these probes are all compatible with Nanoserve equipment with grooves and without grooves. All right, so scanning thermal microscopy module, which is actually the system where you can do the temperature mapping and the topography simultaneously. And this is done by a specialized probe. The probe is should have some sensing element which can sense the thermal properties of the sample. And these thermal properties can be sensed either by a thermistor or by a thermocouple, and there have been numerous type of the probes in the past. There are only two which are in the market now, and I will show you what they are. But just to give a brief of the this our module, we have this probe. The probe is mounted on a for Nanoserve on a half moon washer. It goes to the preamplifier, then it goes to the main amplifier, and that's connected to the AFM. So this is how the general thing takes place. And if you see, this module is compatible with the drive AFM or the flex AFM with the controller. This is a signal input output module for the Flex AFM, but this holder, the Harman washer probe mounted on this can go on a specialized holder where it gets with a magnet. There's a magnet on the back side of this Harman washer, with the metal clip attaches to the magnet on the holder, and you can scan using this. So this is how the whole setup takes place. If you have more questions about this, feel free to ask me in between, or in this Patrick can also help us. Just as a brief history of the thermal probes, the first thermal probe scanning method was invented in 1986 by Kumar Vikramasinghe, and this was a paper published in 1986, and where they were actually getting, this was working like they were controlling a scanning thermal profile using a scanning thermal profiler, where they were managing the thermal flux. Like in STM, you manage the current to image. Here the thermal flux was the one which was being used as a feedback. Then that was the very early stage thermal probe. Then in 93, Arun Majumdar, who is now at Stanford University, they developed a thermocouple with some silicon nitride cantilevers. I tried those probes in 98, 99 when I was at Bruker, at that time Rico. The probes were good. Unfortunately, this was just on a nitride cantilever, so they were bending hues, so they did not succeed much. While this was being done, there was another probe simultaneously which was going in the market through the TM microscope at that time, and this was the Wollaston wire, and which was developed by taking this Wollaston wire. They strip the cloth and expose the platinum element here. This was bent, and you can see this all handmade, and this, so there will be a mirror which will be attached on the back side for the laser reflection, and this will be glued so that the two things can stay together. And this diameter of this probe was about 5 microns. The good part was this probe added so much in the STHM inventions. The people were using this probe even for heating purposes, because this thermocouple, this is a very robust, so you can heat it also, not very high, but you can heat and get a good, you can get a very good thermal conductivity contrast. The big problem was the resolution, and that was the one of the bottleneck for this. As the size of the features was shrinking, this probe could not keep pace with the technology, so it has been now obsolete and nobody else is making those. But the Wollaston wires are still available. One can try to make with hands. This is still possible, but commercially they are not available. Now people have been moved to the microfabricated probes, and this microfabricated probes, this one which is in the market, is from the group of in the Glasgow University, Professor John Weaver is working on this research for a long time, and since 98. These probes are basically silicon nitride. So if you see this image, there is silicon nitride cantilever, and the metal is pattern on top of this to make a thermocouple. So what they do is that they make a pyramid, and in this pyramid, the silicon nitride cantilever is patterned. The one of the problem with this technology is, since the lithography is on a pyramid, this has to be done with the e-beam lithography, and that is this probe requires at least 4 or 5 steps of the e-beam lithography, and that makes it very difficult to make in a simple microfabrication factory. So the silicon nitride cantilever, after patterning, the two metals are coated, so they eventually you get this thermistor, palladium platinum thermistor over here at the end. The biggest thing is to realize that when you make this, the sharpness of the tip is decided by the thickness of the nitride. And secondly, the thermocouple is away from the apex. It has to be inside here, in where the cursor is. So it has to be a little bit down below the apex. So what happens is when you are scanning with the nitride tip and not the thermocouple. So it's away from that. And we are scanning this as the scan keeps continuing, the nitride cantilever wears out, and so you basically are coming, your thermocouple is coming closer and closer. So that changes your any calibration you might have done before starting the experiment, because the distance from the sample to the sensor is changing. So this is another drawback here. The third drawback is this is, as I said, this is silicon nitride cantilever metal. So there is a thermal expansion coefficient much different from the metal. When it go to the high temperature, anything above 160 degrees Celsius, it bends, and it bends beyond use. So you cannot use beyond that. So the poor thermal resolution, the less temperature capabilities, and these are limitations of these probes. So, and that was our motivation to get a new probe which we can scan and on the surface directly. And this was one of the requests made from the data industries. They wanted to use this for heat assisted magnetic recording devices, so that we can use these probes for measuring the temperature of those lasers which are used in those technologies. So this was the motivation for our probe. And this, if you see this next slide, this gives a cross section of the probe. This is the probe actually. So this let me describe this a little bit so that you know what is there inside this whole tip and the cantilever. So the cantilever is made of silicon. And so as the probe, other probe which was made by John Weaver's group, they made silicon nitride, and that was causing a huge bending. So silicon has a better thermal drift property. So we use the silicon. Then there is a oxide on both of the sides so that we make the thermocouple insulated from silicon. So this is thermocouple material 1, and this is a thermocouple material 2. Then we have a proprietary technology where we can make a nanorod using the same metal on the back side. And so this is metal 1, metal 2, and if you see here, the thermocouple junction is right here, and this is a whole thing is from the front is covered with the insulator, and the nanorod comes out of the insulator. So your sample is actually, this nanorod is actually in contact with the sample all the time when you are scanning. And this nanorod, when you see from this focused ion beam image, where I can have a good contrast with the nanorod and the oxide tip, there is a the shining the bright spot is it is the nanorod. So this is at the apex. So you are always scanning with this you are always scanning with this nanorod your sample. So whether you are in a contact mode or non-contact mode, your nanorod is always in the contact with the sample. It means in contact with the thermal properties of the sample. So the cantilever has been designed so that it can also work in a contact or non-contact mode. So the frequencies for the non-contact mode is about 100 kilohertz, and the spring constant is about 10 Newton per meter. But then also we have the contact mode probes, which can be as soft as 1 Newton per meter, and their length is about 375 microns. So they are better for the contact mode probes. So everything has been published in this paper. If you want to get to know more about this, the probe can do the imaging in two modes. As we know, there is one is the conductivity contrast mode or the active mode. In this conductivity contrast mode, basically what is done is that the probe acts as a local heater, and the heating, it can be done by external source or by laser or anything. So basically you heat it and then you see the thermal conductivity contrast. And I'll explain you how does our probe work in this mode. And this is also known as active mode. Another mode is a temperature contrast mode, where we can sense the temperature gradient or temperature change on the sample. If there are samples which are some heated and some non-heated areas, there you can measure temperature, local temperatures, and these are basically like in hot spots. This is also known as a passive mode or sensing mode, because you are not using the tip as an active mode. The thermal conductivity contrast mode applications, normally they are like in a polymer science, where people want to study the matrix of different polymers to see their thermal properties. For example, if you want to study the polymer for making the tires for a car, you would like to mix some polymer which can dissipate the heat when it is going at a high speed, and so that it does not get locally overheated and burst the tire. So they want to change the local properties of those polymers to study the thermal conductivity of the material, and to manage the ratio of the different components. They want to know what is the local thermal conductivity of those components mixed. So this is the one example of the thermal conductivity. Then there are materials like for the thermoelectric materials. They use those materials for the electricity storage or battery, and want to see what is their Seebeck effect, what is their thermal conductivity, what is their electrical conductivity, so that there's a ratio of this the material is controlled to get the maximum efficiency. So these are the various applications of the thermal conductivity contrast mode. The temperature contrast mode applications, they range from the semiconductor hot spots to the newer 2D materials, and I'll show you some of the examples for this both of them. For thermal conductivity, but let's see how this thermal conductivity contrast in our module works. This is what you do is they normally, when you have the AFM, you take the cantilever. This is the actual backside this AFM probe looks like. This the thermal probe looks like. There is a hollow pyramid. The thermocouple junction is right here, and this is the back side of the metal, and the front side is covered with the metal and insulators. The thermocouple is right here inside, embedded here. So in normal tapping mode, you keep the laser away from the thermocouple. When you are using this mode for the temperature measurement, also you want to keep the laser away from the thermocouple. Normally we don't take this precaution when we are using the probe in a topography or other applications, but here this is important, because if you want to measure temperature, you don't want to influence the thermocouple with the laser heating. And normally the laser which is used for the most AFM is like about 1 milliwatt, and 1 milliwatt can raise this temperature to up to about 100 degrees Celsius. So just be careful. Depending upon how do you focus, the temperature can be less or more, but one can easily get 10 to 20 degree temperature increase when you have the laser on the thermocouple. So for normal applications in a temperature contrast mode, you keep the laser away, or you're scanning or you're doing topography, you don't need to move it closer to the thermocouple, which can still work from here. But when you want to move into the thermal conductivity contrast imaging, then you move the laser closer to the pit, so that it comes half of the laser is on the pit, half of the laser is on the flat surface, and it's half of the laser on flat surface is enough to get a good some signal. So you have to have a compromise between the temperature change in the because of the heating and the some signal you are getting. So this is the laser, because we are splitting the laser into the two halves. One is the heating the thermocouple, and another is the giving the some signal for the laser feedback. So when you move it, you can, in our module, you can see the temperature change displayed directly when you're moving the laser. So when you move the laser, this heats the thermocouple, and this temperature you can see in the module. So you can optimize where the maximum temperature comes, and then you can start doing the experiments. The way it works is once you increase the temperature above the room temperature, the thermocouple, now this nanorod is above the sample temperature. So when you're scanning, the probe on areas of the different thermal conductivities, if it is a thermal conductivity more here, it will take the heat from the thermocouple, and temperature will go down. So, and this change in temperature is recorded as a thermal conductivity contrast. So when you are in the area where there is no thermal conductivity change, the temperature will stay where it was originally, and when there's a thermal conductivity is higher, the temperature drop will be higher. So this is how you can record the change in the thermal conductivity contrast through the change in the temperature. The important part is to make a sample, and this is very, very critical. Sometimes if you want to have a polymer, you have a tendency to stick the polymer with on a metal disc, and metal disc is glued with a tape, which is a sticky tape on a stage. That's very bad sample, because there's no, so what the idea is, we want to have the heat transfer from the from the nanorod to the sample and to the disc to the stage, and the stage is our drain basically. So you have to dissipate the heat. Any insulation in between the metal disc or any insulation between the sample. So suppose your sample is on a silicon, and you want to stick on a metal disc, then don't use the tape in between, because this tape is going to stop the thermal conductivity, the temperature, the thermal heat going from the nanorod to the stage. So it will limit the contrast. I normally use the conducting epoxy like silver epoxy, so that I get a better heat transfer. So, and I saw the big change as soon as you move from the conducting this adhesive tape to the conducting epoxy. So just if you are using this technique for thermal contrast, no matter what kind of a STSM system you use, this is important to have the no adhesive tape in between the probe and the stage. So this is the thermoconductivity contrast. We did some images, like this is one of the bismuth tellurides used for those thermoelectric materials. And if you see these this is like a bismuth telluride and carbon nanocrystals. They're coarse putted together and then heated. Once they heat, you can see in topography, you don't see those these grains which you can see here in the thermal image. And this is like a zoom in of those. So if you zoom in further, you can see there are the grains. Now these grains, I don't know if they're real grains or this is because of topography, but the thermocouple is very sensitive. That is, even if it's a nanometer, the temperature change is huge. So you will see the grains in the thermal image better than the topography. In topography, it does not go in, the tip cannot penetrate inside those grains. You cannot see clearly, but you can see those grains very clearly in the STSM mode. So this is one of the thermal conductivity contrast mode. There are further studies, the researchers from India, they were working. So I don't know whether they could resolve this and figure out whether this is a real grain or it is just a topography. but this is visible only in the STSM, not they could not see in SCM or other techniques. So this is important. Then this is a gold nanoparticles embedded in the silica cell, and this has been published again in the same paper which I went ACS. The gold particles are in silica cells. This is topography, and this is the thermal image. Now you can see that even with the silica cell, there's a heat transfer through those cells, and that's why you can see the temperature change. This temperature change is not much. It's like a 1.65 degrees Celsius, and this is just a difference in the temperature from this place where there is no nanoparticles. This is basically the silica, and this is the gold nanoparticles. So there's a temperature between these two, and this is like a highly contrast, which you cannot see normally in the topography images. Then this is a simulation with for showing how this is working in terms of the tip sensor and the gold nanoparticles. And as you can see the distance, as you see the changing the distance from here to here, the temperature changes. So basically this is the drops as you at higher and go closer, and temperature can increase. So basically this is your nanoparticle, and this is tip, and this is the thickness of the cell. Then this is another example of the again thermal conductivity contrast imaging. These are the palladium nanoparticles. They are buried under the polymer, and so basically they were laid out with the FIB or E-beam. I don't know how this customer did that, but then they spin coat this polymer on top of this palladium nanoparticles, and again you can see this is topography, and you can distinguish between the areas of the just the polymer and the nanoparticles. So it is the thermal conductivity contrast works very well in this process as well. Now this is the thermal contrast, which is which can be done for different materials. But then the second mode of the operation is the temperature mapping mode. And for the temperature mapping mode, we make a very simple test structure where we can establish your process if everything is working or not. And in this example, what we did is we took a silicon sample. We did the high dose doping on the both sides, and there's a low dose doping here and no doping here. So this is the layout, and this is topography. What we do is we apply some power here, and this is resistance gets heated. So we want to see if this can get heated or not, and we can sense the temperature or not. So then this is this mode in the when we did a tapping mode. This is when the heater is off and the heater is on, so you can see the gradient of the temperature. Since the probe is not in a constant contact with the sample, so you can get a very good gradient on the sample. And so, but if it is in a contact mode and tapping mode, the next slide shows the difference between these two modes. So this is like in tapping mode, this is in a contact mode. When it's in a contact mode, what happens is you are continuously scanning on the sample, so that is making the thermal gradient disturbed by the heat dissipation from the sample to the tip and through the metal lines. So you can see the heated surface. The good part is you can measure the actual temperature, and in this case the temperature is 20 degrees higher than the tapping mode. So if you want to see the gradient, then the tapping mode is better, but if you want to measure the actual temperature, then contact mode is better. For thermal conductivity contrast mode, the contact mode is far better because you want to allow the heat to dissipate from the thermocouple to the drain. So these are two different modes. There are many examples I would give you for this mode, and this one example is from the paper published in 19 with the and this is a where for 2D materials, there is tungsten disulfide and molybdenum disulfide. These are two materials, the 2D materials, where this is AFM and this is the top optical image. If you see, there is what they did is that they put two electrodes here, and they wanted to see how the heating takes place. These are the metal electrodes. So this is where there is a transition of these two. The thin layers are the tungsten disilicide and molybdenum disilicides. They are making so once you pass the current, and you can see when there is no power is fed into this device, and when the power is fed, there is a heating around the vertical junction of this metal and the tungsten disilicide ones. So here and here, these hot spots are there. The WS2 gives more hot spot than the moly ones. So this is the one example of the measuring temperature in an active device in the hot spot measurements in the 2D materials. This is the same structure with the grain boundaries especially, and so you can see those grain boundaries. There is again the same way where you have those grains and you are powering them, you get those hot spots, and the temperature change is like, say, it's like 1 to 2 degrees, but it's the thermocouple probe is so sensitive that you can detect those. And this is just a factor of this different powers are fed. So you can see as the power increases, the temperature also increases in these devices. And this from the Northwestern University group. Then they were also working on to detect temperature on some of the nanoparticles, and these nanoparticles, these are the magnetic nanoparticles. The idea was they can use these nanoparticles into and heat them with the magnetic field which is generated around this, so that the magnetic field increases the temperature of these nanoparticles. And the applications are like in therapeutic applications in the when they want to use the, let's say for example, you have some people have the treatment for the cancer cells, especially the skin cancer. They put those nanoparticles and then they bring some magnetic field and heat them locally, so that you can increase the temperature enough to burn those cancer cells. So this is one of the examples, but there may be other different examples. So this was so they developed this magnet coil and heating, and then measure the temperature of this. So this is the example of those experiments. These are the magnetic nanostructures. This is just the topography and the temperature. You can see the temperature is like, say, increases from 10 to 50 degrees Celsius, as this is like a 21 degree scale, but this is topography. They know this thermal profile is 50 degrees, and the distance. This basically they're taking the scan over here from here. These are 300 kilohertz. This is a function of the frequency in the magnetic field, and this is again there is the two different frequencies of the different magnetic strength of the particles. So as you increase the magnetic strength of the particles, the temperature also goes up from 14 degrees to 65 degrees Celsius, depending upon what kind of the magnetic particles are being used. Then another example is this is from the Bristol University group of Professor Kubal, and we made a very specialized probe for him because he wanted to go. These are the HEMT devices, and were made of the gallium nitride silicon carbide. We made a long nanorod which can go, because the topography of these structures is very deep, like you can see from here. It's quite deep, and the thermal probe without these rods cannot go inside, and they have the devices which are here. So they wanted to measure the temperature when they power these devices. So they're powering the devices and measuring temperature. You can see the rise in temperature about 60-70 degrees Celsius when they're powering. So this is again an example that you can go deeper into the nanostructure and still see the hot spots. So this is in the working HMT devices. Then this is a plasmonic devices which are similar to those for the laser, where people are using for the lasers or other applications. But you can see this temperature here is about 360 degrees Celsius, and this is a temperature gradient, and this is being done in a tapping mode, and this is lower. This is also in tapping mode, but they can see the beautiful contrast of this plasmonic device. Then this is a recent paper from a group in China, and what they were doing was they were making this graphene with the bubbles, and these when do the bubbles, they designed to make these bubbles, and they were using to measure the Joule heating and Peltier effect, and through the thermocouple probe. This is the same probe which we have developed they're using, and as you get the two bubbles are closer, the temperature goes higher than when they are away, when they are farther away. So this is the controlled effect of the graphene and this is basically they are studying how the heat dissipation will take place if the graphene is used as a material in the devices. So this is the newer paper. Then the latest paper is another one in a that's like a gallium arsenide device for terahertz applications, where they designed this device. There's a device layer, is the metal layer, and they're studying with the application of the high frequency sheath where the heat is generated, and these are the heat generated measurements in this paper. And this is the recent one. So if you want to see this, the more details, this paper is available here. When we are doing this temperature measurement, it is critical to see how the temperature is calibrated in this thermocouple. So we have a microheater thermocouple calibrator which can calibrate the thermocouple, and this is a integrated thermocouple and the heater assembly. This assembly is on a glass substrate so that the heat is localized. So the whole idea was that we want to localize the heat and go to high temperature. So that's why we want to have the insulating surface substrate, and we don't want to have a heater which can heat the whole stage and can impact your scanner. If the heater is a very large dimension, it can even destroy the scanner. So the close-up of this is shown here, where there is a heater and the thermocouple material is basically laid down on top of the heater. So now this thermocouple is getting heated with this heater. So we calibrate. So we take a calibrated thermocouple and we calibrate this thermocouple with that heater, and now this is ready for the testing and calibrating the thermocouple probe. So this is basically three-step calibration. We calibrate this. You have this calibrated thermocouple and integrated heater assembly, and then you use these two in conjunction to calibrate your thermocouple probe. So the whole process of calibration takes 5 to 10 minutes, but it looks like more elaborated here. But it's very convenient to use through this. You can set the temperature, you can calibrate, and the whole system has a way you can find the calibration factors and use this to get the temperature calibrated from the thermocouple display unit. So this is how you can do the complete thing of the temperature calibration, hotspot measurement, and thermal conductivity. This, in summary, these probes, this module can be used in a conductivity contrast mode. It is not for thermal conductivity quantification. That requires, some of the customers have used different ways to do that. So you have to have a calibration standard and do what is the change in the voltage from on the same sample, same place. It can be done, but it requires more. We don't have the process, but it can be done. The probe and the unit is compatible, and they can do. It can do the quantified temperature contrast mode. You can measure the actual temperature if you calibrate it. The maximum temperature which we have seen is can go up to 700 degrees Celsius, and the lateral thermal resolution is, we have seen 20 nanometers, but regularly we can see 50 nanometers. Then you can use these probes in a contact mode, non-contact mode, or hybrid mode of operations depending upon your applications. Sometimes the hybrid mode where people want to have the intermittent contact with the sample in some ways, so you can do those also. All this unit is compatible with the AFMs from the Nanoscale with the mounted probes, and they have a specialized holder which can go with their AFMs. Their laser is excellent. They get beautiful images with the thermoelectric contrast. With their new drive AFM, which is very exciting, I want to show you this because and when I saw this image of the drive AFM, especially that has a inbuilt laser, I don't know you have all the data or not, but that's very attractive for heating the whole thing which we are talking about. So you can do a lot of research using their drive AFM, and you can do basically you can do STHM, thermoelectric contrast at high temperature, elevated temperatures. There are very little papers on those, so you can use this in many ways instead of using the conventional laser. If you have any questions, please let me know. Otherwise, thank you so much for your time and attention.
Thank you, Ami. That was, well, at least to me, very enlightening, and learned a lot about STHM. I hadn't been able to hear so much about it so far. Fascinating. It opens up a whole new way of looking at materials and different kind of way of creating maps on surfaces. And of course, also thanks for your high praise regarding the drive AFM. It's good to hear that you like it.
Oh no, this
so
is
Patrick here as well. Good. So
Yeah.
should we get to the questions?
Okay.
So first I have here in the queue is, yeah, I actually also was thinking about that. What is the highest temperature that you've been able to measure?
So we measured 700 degrees Celsius using those plasmonic devices, and but I have used some of the laser where temperature display was going up to 1100 degrees Celsius, and it can go, but I don't know whether that was just the actual temperature or was a artifact of the study. So I cannot say for sure, but this thermocouple material is compatible to go up to 1100 degrees Celsius.
That's amazing.
That's a lot. That's a lot, yeah. And then I guess this is a follow-up. Oh, sorry, go ahead, Patrick.
Yeah, we might have the same question. I mean, if you have talking about the highest temperature, what is the opposite? What is the lowest temperature you can go?
So
that's the next question in queue.
Yeah, so these thermocouples are linear in the lower range, non-linear are about 200 degrees Celsius. So if you go below temperature, one of the customer is studying the Peltier effect at a low temperature below zero. One of the problem is to get a sample where the temperature is low only locally. If the temperature is low in global, then the reference thermocouple reference junction in the cantilever, because our reference junction is also on the cantilever on the chip. So if you don't have the reference junction, you cannot measure the temperature. So you have to have the.
Then you'd only be measuring the relative temperature to your reference. Then in that case.
So and our reference is also sitting on the chip. So we have to move the reference out of the chip, and then you can do the local temperature. So that is the limitation of the experiment setup. So if you can do that, yes, it can go and it can measure the lower temperature also.
Great. Very interesting. I think this one might be less complicated to answer. On which nanosurf instrument is this available, Patrick? That one's for you, I think.
Yeah. So there I can separate it in two parts. On the scan heads, it's compatible with the Flex AFM, the Core AFM, and of course with our new flagship with the Drive AFM. For the controller wise, it works with the EasyScan 2 controllers, with the C3000 controllers, with the C3000i controller, and also with the new CX controller. And for the EasyScan 2 and C3000 controllers, you will need a signal access module, as Ami has shown in his presentations. And for the CX controller and the C3000, it is enough software options to get the signal I/O activated. And then you can monitor temperature or thermal conductivity parallel to the topography.
Great, thank you. I guess that answered that question in detail. Here's a bit of a longer one. Thank you, Angelo, for that question. Patrick and Ami, we have been using the thermal module with our AFM. We would love to see a reusable holder instead of the half moon holder. I think this would also drive more sales. So is this something you were planning to develop?
So to me, this question is to me or to Patrick. There is a way we can help. It can be developed. So the answer is we are using two different companies where we use the reusable holders, where you can just take the probe like normal, and all we need is two contacts. Since we are measuring the temperature, there's no current flow. It's very easy because we're measuring just the voltage. So all we need is two contacts on the top, and but that needs a clip. So if we can have a clip isolated, we can have one contact on top or one on the bottom or both on the top. That's programmable. We can do that easily. If Nanosurf can do like a holder where we can have a path to going from both the top, two from the top, or one from top and one from bottom.
Okay, yeah, that's something we would have to look into, what that means for the cantilever holder design. Technically, it sounds feasible, but
possible, yes.
Yeah.
I think this is a service or development discussion. So, Angela, I think maybe send us an email to any of the addresses you have, and then we'll contact you and see if we can work on that together, maybe. Moving on, what hardware, software is needed in addition to the standard AFM setup to be able to measure this?
So this hardware is one module, and there's no software needed, extra software. I think all we need is a BNC connector, and the Nanosurf, the IO module or the controller has everything. I think Patrick can elaborate more on that.
Yes, so as said before, the EasyScan 2 controllers and the C3000i controllers, they need the signal I/O module, and for CX and C3000i, C3000, it's a software option to activate the signal I/O.
Okay. Is it compatible for force distance or indentation measurements while taking the temperature data?
Yes, many people have then the temperature distance, like the force distance. We have done force temperature distance also, so that can be done.
Good. So we have plenty of time for a few more.
Yeah, perhaps I have a question, Ami. Can you comment on the compatibility with liquid? Is it possible to do measurements in liquid with them?
Yeah, so there is a possibility, and we are working on this. Maybe I don't know if I'm allowed to say that, but I think there is a possibility, and I let some of your users say if they allow you to speak. But yes, we are exploring that possibility.
That is great. I guess that would open also the way into life science, biology, or chemistry.
Yeah, this is our one of the target to get that, and we have seen it works locally. We have developed the prototype things, but we are still in the process of establishing the protocol and getting those probes tested.
Yeah, that would surely give us a lot of new fascinating experiments. Can only imagine. One more question, Q. So if anyone else has a burning question, now is the time to send it to us. How much does the readout laser interfere with the temperature measurements?
So the readout laser which we are using, as I mentioned in the talk, that the laser, if you're using about 1 milliwatt, that's a normal laser power in most of the AFMs. The temperature can go, if it's well focused, the temperature can go as high as 100 degrees Celsius. So if you, and normally it is not that focused, it's out of focus, so temperature can easily go 15-20 degrees Celsius. But for measuring the temperature, you have to keep the laser away from that. And if you keep it continuously on, the temperature will definitely change because of the heating of the everything. So you have to allow the either the stabilization of the temperature, or just you should, depending upon the experiment. Yes, it can interfere, but it can be minimized.
And is the amount of interference known, so you could sort of calculate and adjust for it?
So no, one of the things that is, so for example, if the measurement is for the thermal conductivity contrast, then you are actually interested in measuring the change in the temperature. So whatever the interferences remains in the noise. So your main change comes from the thermal conductivity difference. So for the thermal conductivity, you can, there is only your interested in any change like 1 degree, 2 degree, 5 degrees. But for temperature measurement, just keep it away so that you can see what is your temperature to start. So you can just bias that in your measurements.
Okay, thank you. I think I got it.
Those temperature increases, and also what you mentioned, Amy, with the drive AFM. And when we got your system here to test it, we put it in the drive AFM, and we wanted to know how much our excitation laser for photothermal excitation is actually heating the probe. And if it's at the base, it's only, I think it's less than a degree, or about a degree or so. If we bring it to the tip, we even got, I think, to 200 degrees Celsius. So we really got a decent increase, which is also then interesting for polymeric samples, I would say.
Yeah, you can use it for many applications.
So that's what you guys do in the app lab in the basement. You just see how hot you can get.
And that's why I got excited about this whole tool.
Okay, it seems you guys have answered all questions anyone was able to think of. So shall we give everyone 5 minutes back into their busy schedules and call it a day?
All right.
So no more urgent questions, and
nothing else coming in.
Feel free to contact Amy, or if you take the info and then put NanoSurf instead of App Nano, that's also there, then you can also address it to us. And we are happy to answer more questions.
Thanks to both of you for taking the time. Thanks, Ami, for getting up so early. It was interesting to see the sunrise in the background.
Sure.
And thanks to our attendees. I hope this was valuable to you. And yeah, this has been recorded. You'll be receiving a link where you can watch it again. And with that, have a great day. See you next time.
Thank you.
Bye,
Thank
everyone.
you. Thank you.
Bye.
Bye.